Okay, here I'll talk you through the solution. Okay, my name is Colleen. A node without any blank is called a blank. So a node without any children is called a leaf. Examples in the tree on the right of leaves are 1, 4, 7, and 13. 1, 4, 7, and 13. Okay, in a BST, a node can have blank, blank, or blank blanks. Here, the answer is children, and a node can have 0, 1, or 2 children. Okay, the height of the tree on the right is, and we use the definition of the number of edges in the longest path starting at the root. So here, the height of the tree on the right is going to be 3. The height of a tree with no nodes is actually going to be -1. And you can imagine if you have a tree with just one node, the height is 0. Okay, all nodes in the left blank are less than that node. That's the left subtree. All nodes in the right subtree are greater than that node. We do not put duplicate keys in a tree. In the tree on the right, the node 8 is the blank node. So it's the one at the very top. That makes it the root node. Other than the blank node, every node has one. Okay, so other than the root node, every node has one parent. Referring to the tree, we can think of 3 as the blank node of that subtree, as the root node of that subtree. So that subtree has a root node at 3. The tree on the right could represent a set of numbers, but if we want to have the binary search tree represent a dictionary, we would have both a key and a value in each node. And then when we search within the tree, that's either to insert something or to find something, we use the key. And again, this picture only shows the keys of my binary search tree, but most frequently we use a binary search tree to represent a dictionary that's mapping between keys and values. We only ever add nodes with insert as a leaf node. We find that they're not there and then we add them as a leaf node. Okay, and then describe the algorithm for deleting a node that has 2 children. So that's our trickier case. It's easier to delete a node if it has only 1 child or 0 children. So what we'll do is we'll find the node just bigger. So if I wanted to delete the node 42, I find the node in the tree that's just bigger than it. And I know that things will be in the right subtree, and that'll be the smallest value. Sorry, the smallest key. Remember, because we use keys to navigate the tree. Okay, so we find the node that's just bigger, and we delete that node. And then we use that node's key to replace the node we're deleting. Okay, let's look at the back side. Okay, let's trace through these. So inserting 0, it's smaller than 8, smaller than 3, smaller than 1. There's no subtree there, so I add the 0 as a leaf. Insert 9, it's bigger than 8, smaller than 10, so I add it to the left here. Insert 100, it's bigger than 8, bigger than 100, bigger than 10, sorry, bigger than 14, so I add it to the right here. Okay, insert 5, smaller than 8, bigger than 3, smaller than 6, bigger than 4, so it's got to go to the right of 4, so I add the 5 there. Insert 11, it's bigger than 8, bigger than 10, smaller than 14, smaller than 13, so it goes here to the left. Okay, delete 7. I need to find it first. So it's smaller than 8, bigger than 3, bigger than 6. I find 7, and it doesn't have any children, so I can just delete it directly. Delete 13. It's bigger than 8, bigger than 10, smaller than 14. I find it here, and it doesn't have any children, so I can just delete it directly. Delete 10. It's bigger than 8. Okay, here I found it, the node 10, and it has just one subtree. So what happens is instead of 8's right subtree being 10, 8's right subtree is going to be 14, and we remove that 10. Okay, similarly deleting 14, it's bigger than 8, bigger than 10. Okay, there it is at 14. It only has one child, so again, I'm going to replace it with its child. So 10's right subtree is going to point to 13, and that 14 gets removed. So again, 13 is the right subchild, sorry, the right child of 10. And check it out, even when we were in the case here where 14 became the new right child of 8, 14 still could have a bunch of nodes on it, and you could imagine that there's like an 11 here and a, gosh, 13.5 or whatever. So this delete 14 shows us the simplest case, but we can actually have a whole subtree there. And even it could have had, you know, 100 over here and 90, like we can have a really big subtree that now that 14 replaces the 10. Okay, delete 6, it's smaller than the 8, bigger than the 3. Okay, here's the 6, and it's got 2 children. That's our trickiest case. And we're gonna replace the 6 with the thing that's just bigger than it. So we look in the right subtree and find the smallest thing, that's 7. We recursively delete that, and then the thing that replaces that 6 is our 7. Let's look at another example. Delete 3, it's smaller than 8. Okay, here it is, and I've got a subtree. So I've got 3 has 2 children. So that's my trickiest case. I'm gonna go into the right subtree and find the smallest value. The smallest value in the right subtree is 4, so I'll recursively delete that and then replace the thing I'm trying to delete with that value 4. So I replace it with the thing just bigger than it. Okay, what if I'm deleting 8? It has 2 children, so that's my trickier case. I'm gonna go to the right subtree and delete the thing that's just smaller than it. We already looked at how to delete that 10. That's the thing, sorry, just bigger than it. And we had already looked at how to delete that 10. Remember when we deleted the 10, 8's right subtree was now gonna point at 14. And so to delete the 8, we delete the thing just bigger than it, which is that 10, and we use that 10 to replace the value. Place the key at that root node.